All right, I think we're all set. Good morning, everyone. Uh, I think this is where we were when we ended off. We were in the middle of discussing certainly one of the most famous experiments in all of physics, Rutherford's gold foil experiment. It led to the discovery of the atomic nucleus. Doesn't get much bigger than that in terms of discoveries. The idea was that he had alpha particles sent towards a very, very thin gold foil. This was before the days of particle accelerators, what they used to call atom smashers. That machine had to be developed first. That first of those machines had to be developed by a couple of his junior associates. But he used radium as a natural source that could be directed towards a very, very thin gold foil. Why gold and why thin? Gold is heavy. Gold has an atomic weight of in the 200s, and gold, of course, can be made very, very thin. He was hoping to make the gold foil as thin as possible so that the number of gold atoms that were being met by the alpha particle was as thin, the layer as thin as possible, because he's trying to probe what the gold atom looks like. And as we know, as was predicted by J.J. Thomson's plum pudding model, the vast majority of the alpha particles went straight through, unmolested, undetected. I'm sorry, not detected, but knocked off course. Some of them had a little bit of a side from its straight trajectory, but most of it went in a very, very narrow range, which looked like very much confirming the Thomson model. But Rutherford, being Rutherford, he just had an instinct. He told his experimenters, Hans Geiger was actually running this experiment for him, part of his very large team, and he had a young associate working with him, Marston, fine New Zealand lad, typical Rutherford man, good soccer player. And he told Geiger to go ahead and check for very, very large deflections from the straight through. In fact, take a look to see if something is coming virtually bouncing back. Really kind of a crazy idea, because almost everything was going straight through. So that's what the boss wants, which the boss gets. Geiger has Marston go ahead and swing the apparatus around, the detection apparatus around, to see, in fact, any of these alpha particles are, in fact, coming virtually straight back from this very, very thin gold foil. And indeed, they discovered that is the case. Just a remarkable story. And the evidence, the observations here are that, in fact, yes, most alpha particles do travel straight through the foil undetected. That is what was found over and over again. So therefore, the atom is mostly empty space. One can certainly conclude that. Some alpha particles are deflected by small angles. Well, okay, that shows that the nucleus is positively charged. That is, there's a resistance going on, a deflection. We know the alpha particles have a +2 charge and a mass of 4. And so if it's being deflected by the atom of the gold, then we know that this thing, whatever is doing the deflection, even the small one, is also positively charged, because like charges repel. If the gold atom, the alpha particle was meeting some kind of a negative charge, it will be absorbed into it. In fact, it was being deflected away from it. And finally, the incredible discovery that occasionally an alpha particle was knocked virtually, some of them straight back, as if hitting a wall and being knocked back. What that told Rutherford was that the atom had a tiny, small, very heavy positive center. Why small? Because most of the atoms didn't meet it. I'm sorry, most of the alpha particles didn't meet it. They went straight through. So it was obviously very, very small. It was clearly the positive charge, because that's what was knocking back the positive alpha particle. And it was very heavy because, yeah, it was knocking back this very fast moving, relatively heavy compared to an electron. An alpha particle, right, is 8,000 times heavier than the cathode rays that were first being bombarded back in the old days. This is a relatively heavy particle, and it could be knocked straight back. So the mass, the weight of the positive charge that was doing this had to be quite heavy not to be knocked itself, to be acting like a wall. The famous quote that you'll hear all the time was in one of the films that I recommended, was he said, "This was indeed one of the most remarkable experiences of my life," Rutherford said, "is as if you had shot a 15-inch shell." This was a kind of a World War I vintage kind of large cannon, into a piece of tissue paper, and the shell came right back at you. That's how surprising. Although he's the one who asked for to check it out. So something there is just, that's Rutherford. Just such a brilliant experimenter, such a creative experimenter. I thought, and it was shown that, in fact, this is where we get that number that we had in our very first presentation, when we're just looking at general sizes of things, that the radius of the nucleus is 10,000 times smaller than the radius of the atom. I told you that in our first class. I thought this might be a nice opportunity here to go through a little bit of math to show why that's the case. You know, guys, when you present science, and I, was a teacher of science for many, many years before I retired. I was a high school physics teacher and a college instructor, that mostly in math and computer science, not physics. There I was doing my regular day job as a physics teacher. There are three ways to present scientific information. One is you can just be told this is true. Good example. The radius of a nucleus is about 10,000 times smaller than the overall radius of the atom. You can be told that, okay, and that's valuable. There are many things, in fact, that you have to be told, because to explain it is just you wouldn't have the background for it. Not you, but the person trying to learn this stuff just is not prepared to follow the argument. So, okay. It's a fact that's to be told, and you move on using that fact. The second layer is to show the experimental evidence that's the case. All scientific facts have to be ultimately backed up by experimental evidence, observational evidence in its widest form. Some things are learned just by casual observation. It is true that the sky is blue. Okay, you don't need an experiment for that. But here, coming from that, the genius of Galileo, that you can take nature and create an artificial situation and run a phenomenon, a process artificially, purposely, artificially, something that you don't do all the time, to try to extract from nature its fundamental principles, how it works. This is the basic idea of an experiment, as opposed to casual observation. Here is a classic, one of the most famous experiments in all of physics. Certainly a very, very artificial situation. And the third thing you can do, the third level of explanation. So we just went through the the experimental evidence to lead to the conclusion that there is this idea of a nucleus, that this is small, heavy center, positive center in the atom. Okay, and I've given you the experimental evidence for it. Pretty convincing. But what about this number? How is it that we know that the nucleus is 10,000 times smaller than the atom? I thought we'd take the opportunity to show why that's the case. As opposed to just saying it, we actually have the wherewithal to do that. And there's a method to my madness to do this, because the ideas I'm going to present here will become very important for us as we look at the Schrodinger equation for quantum mechanics. So here's our situation. We have a gold atom. Its size, we're using modern numbers, the atom itself out to the electron is out there, is 10 to the minus 10 meters, okay? A 1/10 of a nanometer, also in the old days known as 1 angstrom. You'll still see that around. And some of these alpha particles, as you can see, are being knocked straight back. Can we calculate how close the alpha particles get to the nucleus? That would be a measure of the skin, the shell of the nucleus. How far can the alpha particle penetrate into the atom before, in fact, it is knocked back? It's not clear that we can actually talk about the skin or a surface of a nucleus, just as you really can't talk about the surface of an atom. But this is a measure. This is a measure of, given the energy of these alpha particles, how close does the nucleus allow the alpha particle to get before it's knocked back? Can we actually calculate that? Okay. And in fact, we can with introducing the ideas of energy, kinetic and potential energy. So let me give you an exact analogy. The situation, I'm sorry, before we go to the exact analogy, the situation is we have the kinetic energy of the alpha particle. It's 1/2 the mass times the velocity squared. That's the formula for the energy of motion. Its main ingredients are the mass of the particle that's moving and its speed squared. We call this the kinetic energy. And the question is, given that kinetic energy, how close can we get to the nucleus before it is stopped and knocked back? The question is exactly analogous to taking a ball and throwing it up in the air with a certain kinetic energy, with a certain speed. And you ask the question, how high does it get before it turns around and comes back down? These questions are exactly analogous, because just as the alpha particle is meeting a force that's pushing against it, not allowing it to get go on forever, it's meeting a force that's getting greater, till finally it's stopped. The same thing is happening with the ball. The ball is now meeting a drag force, a force being pulled down by the gravitation of the Earth. And as it rises, it will lose kinetic energy, being sapped by this force, which is pulling and pulling and pulling until finally it gets to the top where it has no kinetic energy left at all. It's stopped. Its velocity is 0. Is the energy gone? Not at all. Not at all. Energy doesn't disappear. Energy has gone somewhere. It's gone into a concept called potential energy. Oh yeah, that ball up there definitely has energy. If that was a bowling ball 20 feet above your head, you would not want me to just simply drop it and let it fall on you. That would not be good. There is a lot of energy in that ball up there, and the measure that energy is called potential energy. And the way we measure that energy in a gravitational field is the equation: the mass times the acceleration of gravity, which is always used little g, times the height of the ball, whatever the height is. So if the height of the ball reaches this maximum height of h, this would be the maximum potential energy that the ball would attain. This is where all the kinetic energy has been sapped out and gone into the potential energy of m times g times h. G, by the way, is 32 feet per second. Okay, it's the acceleration of gravity. In SI units is 9.8 meters per second. And so if the kinetic energy has been all sapped and gone into potential energy, then therefore we can set these two equations equal to each other. And we can actually solve for h. H is equal to v squared over 2h. Notice that the m's on both sides cancel out. This equation makes sense. Certainly, the greater the velocity, the higher the ball will reach. Matter of fact, it's very powerfully associated with that. It's determined by the velocity squared. Certainly, the greater the pull of gravity, the less height, the smaller the height can be reached. If I were to throw this ball up with a very powerful G, like for example on Jupiter, with the same speed, it wouldn't go so high. If I were to throw this ball up on the moon, surface of the moon, which has a much smaller G, it would go much higher. So this equation makes sense, that the height, the maximum height of the ball would be determined by these kinds of factors. Let us do exactly the same thing using the conservation of energy with our alpha particle heading in straight in towards the, now what we understand is the atomic nucleus of the gold atom. By the conservation of energy, the kinetic energy of the alpha particle must equal the maximum potential energy that can be reached upon very close approximation of the alpha particle against the pushing force of the positive nucleus of the atom. Okay. We can set that equal to each other, just as I did here. Here now the potential energy is a different equation. Again, I ask you to trust me on this, that the potential energy approaching the central body of the nucleus is equal to a constant, very similar to the G constant in the other case. Here's the charge on the alpha particle, here's the charge, positive charge on the atom, and here is that distance. This is the distance, and when I set them equal to each other, I should get the minimum distance. Well, this number is 4. I'm sorry, this number is 2. This is the positive charge of the alpha particle. This here is 96, the positive charge of the atom of gold. This here is the mass of the alpha particle. This is 4. I know these numbers. Just as I did over here on the left, I can solve for D. I can solve for that closest approach given the energy of the alpha particle. Relatively simple algebra to isolate D. And again, if you look at the formula, it makes sense. Here again, we have a couple of constants, but the greatest separation distance is certainly proportional to the charges, the positive charges on the two objects that are being pushed together. The greater this product is, the bigger the minimum distance is going to be. They're not going to get so close if those numbers are very, very big. Okay? So it makes sense that these numbers are in the numerator. It makes sense that the mass of the alpha particle is in the denominator. The greater the mass of the alpha particle, the more it's going to penetrate in. The smaller that D is going to be. And certainly the faster I can shoot that particle into the nucleus, into the atom, it doesn't actually get into the nucleus, but into the atom, the greater the kinetic energy, the greater the velocity, the more that fraction will go down with the bigger and bigger the distance of closest approach will in fact get smaller and smaller. Well, I know all these numbers. Okay? K is the constant for electrostatic charge, and this number here is 2. This number here is 96. This number here is 4, and the velocity can be measured, right, to get the kinetic energy. So in fact, we can do a calculation, and that's where we get this number. That's why we say that the nucleus is 10,000 times smaller than the atom. Okay? You take just in terms of orders of magnitude, 10 to the minus 10th, which is the size of the atom, divided by 10 to the minus 14th, which is now a measure of the size of the nucleus, you get 10 to the 4th. It goes in 10,000 times. So the third level of explanation, I can't do this too much for 2 reasons. One, it would take a lot of time to do this in every case. So as worthwhile and as interesting as it is, if we had more time, we could do a lot more of this. So I need to pick and choose when I do this. But I thought this was a nice opportunity to take to start this kind of analysis. And we'll try to do a bit more as we go on. I realize that this kind of math is not many of your cup of tea, so you don't need to worry about what we just did. You've lost nothing by staying at the top 2 levels. That in fact, we do know that this is the case, that the atomic nucleus is much, much smaller than the atom itself. And in fact, we even have a measure of it. It's about 10,000 times smaller. Those are important facts. And you know the experimental evidence of why we believe that. The mathematical analysis is maybe one level that you don't choose to worry about, and that's just fine. So here is the famous so-called planetary model of the Rutherford atom, and the first thing we can see what's wrong with this picture is certainly not the scale. right? What happened to the 10,000 times small? Okay? So it's not to scale. The other, the other part of this is that if the nucleus contains all the mass and all the positive charge, then these electrons, which we know are there, right, from J.J. Thomson's discovery, they're somewhere. They're not in the nucleus, so they're someplace else there. The traditional idea is they're circling around. Rutherford knew that they were not circling around like planets. Okay, it was this comes from the historical idea of the Bohr atom, which kind of people retrofit onto Rutherford's atom. Rutherford said, I was perfectly aware when I put forward the theory of the nuclear atom that according to classical theory, electrons ought to fall into the nucleus if they're going around and around. I'm going to show why that's the case in our next presentation. So let me move on to our next presentation and say why this can't be so. Why the electrons cannot be circling around the nucleus like planets going around the sun. This could never be the case, at least according to classical physics. And Rutherford, in fact, never put forth a planetary model like this. Okay, last idea of this presentation is we get after the idea of atomic number. Atomic number. Look at the periodic table, guys. How is this put together? How is this fantastic table put together? In two ways. One, we start listing the elements in atomic weight. Right? We can weigh the atoms relative to each other, and we simply begin to list them as the weight gets bigger and bigger. And we keep an eye on the chemical properties. So we make sure that all the alkaline metals are in one column, and all the halogens are in this column, and all the noble gases are in this column. We keep an eye on the fact that we have families of common chemical properties, and that's what makes us stop at this place and start again over here. But we keep the atomic weights in order. That is, if you want to stop with neon over here, then the next element that you want to put is the next heaviest element after neon, which is sodium. And in fact, it is the next heaviest element, and it falls exactly where it should be as a alkaline metal. It's an incredible pattern. Incredible. Where this comes from. This is one of the great objectives of our course, is to try to understand where this incredible pattern comes from. What we're going to see right now is that when you just simply list the elements given this pattern of atomic weights and properties, letting them fall into these natural columns, if we just simply list the numbers, just call this guy 1 and this guy 2 and this guy 3 and this guy 4, these numbers are being dictated by the table. The table is now dictating what we call the atomic number. It has no physical significance except it is the order of the list that the periodic table dictates. I'm beating this idea to death, guys, because we're going to discover that this, in fact, has a very, very profound and deep meaning, what these numbers are. And most of us, already know what I'm getting at. It was proposed by an amateur by the name of Antonius van Block, and what he proposed was that the atomic number, hydrogen being 1 and helium being 2 and lithium being 3 and sodium being 11 and uranium being 92, gold being 96, that atomic number was in fact equal to the positive charge of Rutherford's nucleus. Just as the alpha particle had a positive charge of 2, what these numbers are telling us is that this is the positive charge contained in Rutherford's new heavy positive nucleus. The weights, we know that electrons weigh virtually nothing, so the weights are all in the nucleus, the atomic weights, which are dictating how this table was strung out in the first place. But the positive charge that we've now discovered, that is what pushes back the alpha particles, That charge is nothing more or less than this atomic number. Incredible speculation. Of course, it sounds trivial to us because we learned this in middle school, but this is where it comes from. And certainly I want to show you the experimental evidence for such an important concept. And that's done by this young man here, Henry Mosley. You will not be surprised, another postgraduate in Rutherford's lab. Okay? And what he did to discover the connection and why the atomic number is in fact not just some number that's assigned because of a table, but it has a deep physical, is reflecting a deep physical property of the atom, is he used X-rays. And here's our good old X-ray tube. This is how X-rays were first produced, even in the early X-ray machines of medicine. It's still fundamentally produced like this. You take a cathode ray tube, an evacuated tube, you shoot your cathode rays against a heavy metal anode, and we know from Röntgen's experiments that it creates, among other things, not only does it create cathode rays, but more importantly, it creates X-rays. Okay? And given the shape of the anode, you can even kind of direct them going in a certain direction. You have to remember that when you see radiation come off in some kind of a natural process, and X-rays are a type of electromagnetic wave, we'll look at that on the next presentation, that when radiation is produced in a natural process, guys, it is not just one wavelength. It's not just one color. If you want to produce something with a light of any sort with just one color, you need to do that artificially. You need to get yourself a laser. Natural processes, like for example the sun, does not just produce one color. It always produces what's called a spectrum of colors, spectrums of wavelengths of varying brightnesses. And here is our spectrum for the sun. We know that peaks in the visible, most of the light is in the visible, but there is some ultraviolet light coming from the sun. There is some near infrared light coming from the sun. It's the same with these X-rays that are being created by the electrons banging into the various different metals. It's creating a spectrum of X-ray wavelengths. And this spectrum, in fact, was discovered before the time of Mosley. Okay, discovered by a man by the name of Berkeley, another British physicist who actually won a Nobel Prize for discovering this kind of spectrum, not in great detail. It was Mosley who was able to find the more detailed spectrum like this. And it's an interesting looking spectrum, okay, compared to the sun. It certainly has the characteristic bell shape that we've come to expect. Here is the peak frequency of all the X-ray wavelengths that are coming out. Here are a higher bunch of frequencies. Here's a bunch of lower bunch of frequencies. It's what we expect to see coming from a natural process of creating radiation. But it's these spikes which are very unique. We don't have this in the spectrum of the sun. You don't have this in the spectrum of your light bulb. This is strange. This is coming out of the X-ray spectrum when these metal anodes, and Mosley used a series of different metals and created the spectrum of each metal one at a time. He was able to measure accurately this spike. What was the frequency? What was the wavelength of this high spike? That spike, that wavelength changed as he changed metals on the anode, which was the atoms that were being excited to create the X-rays. It's called the unique characteristic frequency. These frequencies here are called the breaking frequencies. These are the frequencies. This is the spectrum that's used in our modern X-ray machines. The spike is filtered out. Oh, it's created, but it's protected from us. It is the first thing that's filtered out from the X-ray machine before they take our X-ray of teeth or whatever, is that this spike, of course, is taken out. It's very, very dangerous, very high energy radiation. So this is the radiation that's controlled and filtered to create the X-ray. But Mosley was able to measure these different frequencies as he went through the various different elements that he could create for his anode, the metal plate that was being bombarded by the cathode rays, by the electrons. And this is what he got. He took the square root of that frequency, that high spiking frequency, okay, based upon units measurement, which are not important to us. He basically took the square root of that frequency that he was measuring, and he mapped it against the atomic number. This artificial number that's being created because of the order of the table. The order comes first, and then the numbers come second. And these numbers, these atomic numbers, are fundamentally describe this spike frequency coming out of all the various different metals. And he did this for, dozens of anything that he could get his hands on to be used as an anode. What this tells us at the very least is that the atomic number is something fundamental. It is not just a haphazard coincidence from the order of the periodic table. This frequency clearly that's coming out of the various different metals by the bombardment of the cathode rays clearly is something fundamental about those different atoms. And what they line up against is the atomic number. Therefore, the atomic number is something fundamental. It is a fundamental characteristic of the atom. Now we need to understand what that fundamental characteristic is, being the Van Brock's speculation that, in fact, what this number is telling us is the amount of positive charge in Rutherford's nucleus. That will have to wait. They will have to wait for how that piece is put together. Because it turns out that Mosley is also working with another young postdoc. Mosley is 26 at the time. He's also working with another completely unknown postdoc, also a postdoc of Rutherford, working in the same university by the name of Niels Bohr. Okay? And he and Bohr have a conversation about Mosley's results. And we'll see where the proof comes in. And Bohr's theory of what this is, what these unique spikes are, these frequencies are in fact telling us what the positive charge of the nucleus is. Okay. Well, I switch gears here. Greg, do we have any questions?
Yes, we have a couple questions about the Rutherford experiment.
Okay.
So Bill was wondering if Rutherford tried any other elements than gold.
Well, gold was an easy one to work with at first. I'm sure other elements have been used afterwards. As we all know, one of the most important things about experiments is they're reproduced. And probably nothing is more reproduced than the gold experiment. But at the time, what Rutherford was using was gold because it could be easily, malleable and easily made into such thin sheets. And so I'm trying to do two things at once, answer the question and find what I'm looking for here. Any other question?
Yes, one more question. Andrew Sherman was wondering if the Rutherford experiment originally was intended to test his pudding model.
Yes, that's exactly what he was doing. Yes, absolutely. He was a student of J.J. Thomson. He now had taken over the Cavendish lab, but yes, he, as most physicists, felt that the plum pudding model was the best model that one had at the time, and he was trying to give more experimental evidence for it, and it was going well, showing that that the atom was mostly empty space, as the plum pudding model would say, given the fact that everything was kind of very diffuse and the electrons were just floating around, not doing much. Okay. Can we get started, Greg?
Could I just, I asked that question, I just wanted to know, in the pudding model, it seems like there's this mass of protons and the
No, no, no
electrons are
protons. No, no, not allowed. No, no, no protons. We have no protons yet. I have not used that word, or you are not allowed to use that word. There is a positive charge.
Yeah,
The atom has a glob of positive charge, which now Rutherford had shown is all concentrated in what's called the nucleus, but we do not have protons. Fair
okay.
enough?
Okay, but the
Okay.
positive charge was diffused throughout the atom in the pudding model, right?
Yes.
So the experiment kind of blew up his whole pudding model, right?
Absolutely.
Yeah, okay.
Okay. All right. So we begin the beginning of quantum theory. And what we're going to be doing for the first half of the slides, you will not be surprised, is looking at properties of light. Because that's where, if you want to know where does the evidence come from the idea of the quantum of energy, it is from the observations, the experiments, the behavior, the properties of light. Okay. So let us look at some of the properties of light. This is kind of a dense presentation, guys. I'm going through quite a bit of high school physics, so bear with me here. I'm not showing you anything that is not absolutely essential background for us to understand quantum theory. I think you'll give me the benefit of the doubt that you realize that very much quantum theory is based fundamentally on the properties and the interaction between light and matter. So we need to know something about light. Okay. One of the things that we know about light is that light waves can go through each other without disturbing each other. Well, they'll interact when they are going through each other, but once that interaction is over, they go through and they go on their merry way as if the interaction never took place. The waves are not disturbing each other in any long-term way. They go right through. Interesting property of light. Particles don't have that property, right? Try to send particles through each other, and they'll bang into each other and get deflected, knock all over the place. The basic properties of light that we learned in middle school science is the law of reflection, the law of refraction, that going from one medium to the other, like from air to glass, or air to water, or water to glass, the light will bend. It'll change its direction. And coming out of the glass back into the air, it'll bend once more. We call this refraction of light. And finally, dispersion. The idea that a prism can break up, a glass prism can break up the light into its colors. Newton's very famous experiment, maybe on the par in terms of it being famous with the gold leaf experiment. Dispersion, notice, is caused by refraction. It turns out that the different colors are refracted by a different amount. So the sunlight, which we now know, is a combination of all the colors. If you send it through the glass, they're all refracted at a slightly different angle, and so they're spread. So dispersion is really not a new property of light. It's a new phenomenon coming from refraction. We will see that there are other ways of breaking up a spectrum into its various different colors, besides using refraction, the one that actually we will be using going forward in our study of quantum mechanics. We need to get some vocabulary straight. Hopefully this is a review that these words are not unfamiliar to you. We have a wave. A wave is not a particle. A wave is a disturbance. It's a pattern of energy. It generally is a medium that's being disturbed. Classic example being a water wave. Another example being a sound wave, where the medium is air. It is a pattern, a vibrating pattern of energy in that medium. And we describe the wave by talking about its wavelength from crest to crest, or trough to trough. Okay, is the wavelength of a simple wave. The crest of the wave is actually, the amplitude of the wave is actually the distance from that flat equilibrium point where the water is not disturbed up to its maximum disturbance, or its maximum disturbance going down to trough. These two distances would be the same. That's called the amplitude of the wave. This is how we measure the energy of a wave. Not surprising. It's not the wavelength that measures the energy, it's the crest of the wave. The amplitude of the wave. Just think of your water waves out in the ocean, okay? It's really not how long the waves are, it's how big they are, where the energy is that can knock you over. Okay, so we have some fundamental vocabulary here. Wavelength, traditional letter is the Greek L, lambda, for a wavelength. Okay, and then we have the notion of the frequency of a wave. Here's a low frequency, a medium frequency, a high frequency. Frequency is the number of cycles that the wave goes through per unit time, per second, per minute, whatever. If you can think of the wave as moving, then it's the number of crests that pass you by at a certain given point. Okay, certainly more crests will pass you by here with this high frequency wave than a low frequency wave. By the way, we talk about low frequencies and high frequencies, not small frequencies and big frequencies. Okay, we literally use the language of acoustics to describe waves in general. We don't talk about big wavelengths, we talk about short wavelengths, not small, I'm sorry, long wavelengths. We don't talk about small wavelengths, we talk about short wavelengths. Okay? So we use this acoustic language for all waves, and I'll be using that language consistently. So a low frequency means a small frequency. Okay, these are general words that I think all of us are very comfortable and familiar with. Very important idea. One of the central important technical things that you have to know and have to be comfortable with. The relationship between wavelength and frequency. It comes through the speed of the wave. In a uniform medium like all of air or all of water, waves move at a constant speed. This is one of those facts that I give you. How do you measure the speed of a wave? A direct analogy. Suppose you have a train of cars, car trains, and each car is 50 feet long. And you're standing on one place on the track and you're watching the train go by, and you see that 4 cars pass you by every minute. That is, the frequency of the train is 4 cars per minute. What's the speed of the train? Well, okay, there's 4 cars, they're 50 feet each, 50 feet along each, so there's 200 feet of cars that pass you by in a minute. So the speed of the train would be 200 feet per minute. To calculation, velocity is equal to distance over time, 3rd grade formula. What's the distance? Well, the distance is 50 times 4, 50 feet, 4 cars, and the time I said was 1 minute. So the speed is 200 feet per minute. Another way to do it. Isn't the speed 50 feet per car times 4 cars per minute? Yeah, it's the same calculation. You calculate the speed of that train by 50 feet per car times how many cars passed you per minute. Isn't that the car length times the frequency? Okay. So with this analogy, and this is a direct analogy, if this formula makes sense to you because of our little analysis here, then you'll give me that the speed of a wave is the wavelength times the frequency. It is exactly the same analysis. Instead of having cars, think of the waves going from crest to crest and having them pass you by with a frequency of f. And so the speed of a light wave, the traditional letter c, the speed of light, is equal to the wavelength times the frequency. Why is this so important? It's so important because the radiation that we'll be talking about is radiation of electromagnetic waves, in which light is just one small piece of that overall spectrum. Those radiation waves will all be going virtually at the speed of light. We'll be working either in air or in a vacuum. And so they all have the same speed. And so they all comply with this formula, that constant speed is always equal to the wavelength of the radiation times the frequency. And therefore, if you know one, you know the other. And you can take this little formula and write it 2 different ways. You can say the wavelength is the speed over the frequency, or you can say the frequency is the speed over the wavelength. They all work. And you're going to have to become comfortable with this because physicists tend to talk about frequencies and astronomers tend to talk about wavelengths, but they are completely equivalent because of this equation. You have to realize that as the wavelength gets shorter and shorter, the frequency is getting higher and higher because they're always multiplying up to the same number. And as the wavelength is getting longer and longer, then the frequency must be getting shorter and shorter. So, because again, the product is always the same. Picture maybe is worth 1,000 words. Let's see if this helps. This is my first little Mathematica demonstration for us. I thought this might be helpful. Here's a simple sine wave, and here's the frequency of 1. Here's one full wavelength. Has a frequency of 1, a wavelength of 1. This wave has a speed of 1. If I go to the next frequency, a frequency of 2, we see we have 2 crests. 2 crests pass within this time frame. But look at the wavelength. The wavelength is now a half. Here's a full wave from the start of it all the way through its cycle to the end. Okay? The wavelength is now a half. Frequency of 2, wavelength of a half, the speed is still 1. So as I continue to increase the frequency, look what happens to the wavelength. The wavelength gets shorter and shorter and shorter. Okay? In this very, very simple mathematical way. With a frequency of 4, we have a wavelength of a fourth because they have to multiply up to the same number. In this case, my wave here, I cooked it so that the speed is always 1. Okay? So this relationship between frequency and wavelength are very, very important. We'll be using it. I'll be using it all the time, and I won't say anything about it. You're gonna have to get used to this. Why do they use this equivalence back and forth? Well, astronomers are interested in things like redshift, how the wavelength stretches, they're interested in the colors of the light. You have the beautiful red color of Antares compared to the brilliant white color of Sirius, the blue-white color. They're interested in the colors of things in their spectrum, and so they focus on what we think of as the color is the wavelength. Physicists are very much focused on the energy, and because of Planck's formula, which we'll come to at the end of the presentation, that the energy of the wave is Planck's constant times the frequency. Could also be written as the wavelength, but the traditional formula is times the frequency. Physicists focus on the frequency of the wave, and the wavelength is secondary. But they slosh around in both cases. You'll see graphs where some graphs have on their x-axis the frequency and some of the wavelength and some of both, and you just have to make this connection that when you know one, you know the other, because they always multiply up. Well, of course, we'll be talking about light waves, electromagnetic waves. Those two numbers always multiply up to the speed of light, 3 × 10⁸ kilometers per second. And since they always have the same product, they vary, inversely. As one gets big, the other gets small. Okay. The next property of light that we need to talk about is diffraction. When a wave goes through a small opening, what do you mean by small? I mean the wavelength is comparable. The size of the wavelength is comparable to the size of the opening. Okay? When that happens, the wave spreads out. Experimental fact. This happens. And the phenomenon is called diffraction. Particles don't do this. You send particles through an opening, they just go straight through. A wave will not. A wave will spread out as it goes. And this is something that we see. There is lots of experimental evidence studying waves that do this. Here's a nice example of it. Okay? So this is the property of diffraction. This property of light will become very important for us. Where are we going? Okay, I think most of you know where we're going. These properties of light, these wave properties of light, will also be properties of electrons and atoms. That particles have these very same properties. This is the heart of quantum theory. This is the great revolution of quantum theory. This is why we need to go through these properties in classical physics that was actually leads to the discovery or the evidence that light is a wave. We're going to turn this on its head by showing that, in fact, quantum particles have exactly the same wave properties. How do you think? How can that be? Well, that's why Feynman said, you know, I think everyone can safely say that no one understands quantum theory. There's no easy explanation for this, but I will show you the evidence that this is in fact the case. So we have this property of diffraction. Last property that we need to talk about right now is the property of interference of waves. Waves will, when two waves are in the same place at the same time, they what we call interfere in a natural kind of way. If a crest of one wave meets a crest of another wave, the medium will be picked up by both crests. It is an energy disturbance after all. One wave has the energy of picking up a certain height. The other wave comes along, it has its own energy to pick up that medium by a certain height. How much will the medium be picked up by? The sum of the two heights. Okay? And that's called constructive interference. So when two crests meet two crests, you will get a very high crest. When two troughs meet two troughs, you'll get a very low trough. And so you get, in a sense, a sum of the two waves. Particles don't do this. When particles meet each other, they just bang off each other and go away. Even more interesting, if a crest of one wave meets at the same place, the same time, an equal-sized trough of another wave, you will get no wave at all. This is certainly something that particles don't do. You can't add two particles and get nothing. But yet that's what you can do because these are patterns of energy. And these energies are moving the medium up and down. This is nothing profound going on here. Okay, one wave wants to move the medium up, the other medium wants to drag it down, and there's a war, and the energies cancel out, and the water doesn't go anywhere. The water is calm at that place. That's destructive interference. This is a characteristic property of waves, and we see it here by dropping these two stones into the quiet pond. As the waves spread out, okay, what you're getting here is classic interference. These circles that you can see, these bright circles, these are the crests. The crests are actually making a lens, and it's concentrating the light. This water is very, very shallow. The light's being concentrated down to the bottom of the pool, and what you're seeing is the light down at the bottom of the pool because the crest is acting as a lens, focusing the light down, and it's focused as a bright line. In between the two crests is the trough, which is acting literally as a dispersion lens. It is dispersing the light, and it's hard to see with our naked eye, but that is actually dimmer than the calm water. That is actually it's a bit darker than the water which is over here, which is not being disturbed at all. Hard to see. Okay? So you're seeing literally a pattern of crests and troughs. Here, again, it's hard to see, but here's where one crest reaches another crest. Okay, right here, there's little bright dots. These dots are actually brighter than the regular alone crests because these crests are higher and they're acting as a better focusing lens. And the light is being concentrated even greater there than in just a single crest. And they're a little bit brighter. Okay. This clearly is not the way these detailed experiments are done, but I wanted to show you everyday experiences, observations as opposed to experiments which verify these phenomena of light. Here's two more. You're looking here at two interference patterns created by reflection. Okay? In a compact disc, we know a compact disc is a series of very tight grooves, one after the other. So therefore, as you shine white light on the compact disc, some of them will be reflected from one groove, and the light will also be reflected by a nearby groove. Well, those two grooves will reflect the light at slightly different paths coming to our eye. And what we'll get is not only constructive interference, but very, very importantly, some destructive interference. Some of the colors will be knocked out. Some of the colors will be deconstructed. so that they don't survive. There's the amplitude of the blue light has been diminished, has been gone. And so when you knock out the blue light that's coming into your eye, what you see is the red and the yellow light. Okay? Here's an oil slick on the ground. We've all seen this in parking lots, maybe in our own driveways. Okay? This again is from reflection. The sunlight is hitting the oil slick, and the top of the slick is reflecting the light to our eye, and some of the light is going all the way down to the bottom of the very, very thin slick, and it's being reflected back into our eye. Again, we have two waves of light because of the two surfaces of reflection coming to our eyes simultaneously. Some of those colors are being subjected to destructive interference. Some of the colors are not there. When some of the colors of sunlight are not there, what we see is the other colors. Okay? And that's why this here is a beautiful violet, because in here, virtually all the other colors have been deconstructed. And the only light that's coming to our eye is the violet or the red. Combination, some colors are being let through and some colors are not here. And so we get the combination of colors. Okay. The idea of diffraction and interference. In 1800, Thomas Young used both these phenomena, wave phenomenon, to show that light was a wave. A really brilliant experiment. He took a prism and he shone light through it and got one color, blocked out all the other colors, sent just one nice color through, red light, and he sent it through two openings, very, very small openings. So he knew he would get diffraction. So the waves, if there were waves, which was his hypothesis, would spread out, coming from these two different holes, because the holes were small enough that you would get diffraction and the waves would spread out. Well, now we have two wave patterns very close together, we will get interference. And therefore we should get some places where we get crests upon crests, some places where we get crests upon troughs, crests upon crests, and also troughs upon troughs, right? Here is the crest of the wave, here's the next crest of the wave, here's the trough. So here's the wavelength. The wavelength is here. Okay? D is the distance between the openings. And so these solid lines are the crests and the dotted lines are the troughs. Okay? Look at where we get a minimum, as it's marked here, deconstructive interference, a dark spot. Here we have the crest of one, the solid line, meaning the dotted line of the other. That is destructive interference. One light wave is trying to, whatever the medium is trying to agitate the medium in a positive way. The other light wave is doing it in a negative way. The energy cancels out and you get darkness. You shine two lights and you get darkness. You can never do that with particles. This is a property of waves. And here is the light dark properties, a pattern of interference. I hope that you watched that video that I asked you to watch before class. If you haven't, please watch the historic double slit experiment. It is a wonderful demonstration of wave interference and a very nice explanation of this, indeed, this experiment. It is a very interesting video, and I really encourage you, if you haven't watched it, to watch it. The other interesting thing about this experiment is taking all the dimensions of the experiment. We can measure D, that's the distance between the opening of the slits. We can certainly measure the pattern of dark and light and dark and light. And we can measure how far away the screen that's producing the light is from the screen that's we're catching the pattern. We can measure these numbers. It won't surprise you that you can do a geometric analysis of this pattern and get lambda, the wavelength, embodied inside the other three measurements of D and L and S. This is a nice exercise that's done in high school physics. This is one I chose not to do. We could do, but we can't do them all. But it will not surprise you. Why are we getting a maximum? Why are we getting a bright spot here? Well, because these two distances are exactly the same. So if the light is coming out at the same time, then right here in the middle, yes, a crest will meet a crest. and a trough will meet a trough. They're the same distance away. Okay, so they will hit the screen at the same time. Here's the next maximum. Why is this? Well, if this is, let's say, 9 light wavelengths away, then this guy might be 10 or 11 lengths away. And again, we get crests meeting crests and troughs meeting troughs. So yes, the pattern is being determined by the lengths, the distances from these openings to the screen, depending upon the wavelength. If the wavelengths match, if the difference between the lengths are a whole number of wavelengths, you'll get crests upon crests. If the change in distance, if the difference between the distances to that part of the screen is a half a wavelength, you'll get crests upon trough, and you'll get destructive interference. So yes, there should be a geometric relationship between these 4 numbers, and indeed there is. And so there is a way to actually measure the wavelength of light through a very simple experiment like that. Wavelengths of light are small, right? 400, 700 nanometers, but yet with great care, using this again is a high school physics experiment that you will do. You won't use a prism, you'll use a laser. You'll cheat and use a beautiful monochromatic, powerful laser light going through 2 close slits, and you can actually get quite a decent measurement of the wavelength of the ruby red laser light. Okay, the last idea of creating this spectrum, I said that you can create a spectrum, you can spread out the colors of light. And by the way, when I say light, I don't necessarily only talking about visible light. Many examples we use are visible light because we can see it, okay? But when I mean light, I mean the whole electromagnetic spectrum. If I really want to say visible light, I'll probably say visible light. And so please use light in this very generic, broader sense. So this is one way of spreading out a spectrum. There's a better way by using diffraction and interference. You can send white light, for example, through what's called a diffraction grating. This is nothing more than a whole bunch of openings, a whole bunch of slits very close together in a opaque screen. Okay? The only light that can get through is the light that goes through the slits. Turns out that will create, through the diffraction of all the light coming out, spreading out, interfering with each other, you will get a beautiful, detailed, coherent spectrum. Actually, you'll get multiple spectrums. This is really quite surprising that the colors won't just be all jumbled up like the oil slick, but you will get a spread out spectrum. Actually, this spectrum is better spread out than what the best glass can do. This is really the way in which light is spread out in the lab using these diffraction gratings. This I cannot show you. This is complicated. We don't even do this in high school physics to go through the detail of how these multiple slots will find a way to just balance out so that you get this beautiful combination of destructive and constructive interference to create the spectrum. This is a little nerdy. What's great about this device to do this is you can use not only white light, but if your grating is thin enough, if the distances between those little openings are small enough, you can spread out anything. You can spread out ultraviolet light. You can even spread out X-ray light. Okay? This is what Mosley used to create his X-ray spectrum of these finely created diffraction gratings that he used. He didn't do it with light, he actually did it with a very difficult to work with X-ray light. Mosley was a brilliant experimenter. Great sadness. If you notice his dates, he died in 1915. Yes, he died in the war. He died as a soldier in the war in Gallipoli. He felt a call to serve his country. He was, of course, a PhD in physics. He was in the radio communication division, but he was sent over with the combat troops. And we know about the slaughter of Gallipoli, and he was killed in that battle. His work was so well known, clearly he would have been on track to win a Nobel Prize, and God knows what he would have done as an experimentalist if he had lived, died at 27, 28, who knows what he would have done. But the British government actually changed the rules of sending scientists into combat after Mosley's death. They actually said, you know, this is a little crazy to send these people into harm's way like this. These people have unique, you know, talents and gifts for the country. They can be better served not being on the battlefield. Okay. Also, I hope you had a chance, if your electricity and magnetism is a little rusty, wonderful video from class 2, the class 2 Wednesday email. If you want to go back to that reference, there's a very short video about the combination of electricity and magnetism. Hope you had a chance to watch it. If you didn't, and this is not enough, it's 4 minutes well spent. For middle school, the two most important properties of electricity and magnetism that we need to remind you of, certainly for middle school, here is the electromagnet. Right? You create a coil of wire and send a current through it, it makes a magnet. You coil that wire around a metal bar and it makes even a better magnet. So this is our good old electromagnet. Apparently a current creates a magnetic field. Well, what is a current? A current is in fact a changing electrical field. These are moving charges, discovered in 1820 by Ørsted. Much more important in a sense, maybe one of the most important discoveries in all of science is electromagnetic induction by Michael Faraday. That if you simply take a coil of wire and expose it to a changing magnetic field, for example, let that magnetic field be created by a magnet which is moving, or let the magnet stay stationary and move the coils, but submit the coils to a changing magnetic field and you will create an electric field. You can create an electric current in the wire. Okay? And this, of course, is our whole electrical age, the idea of a generator. These are the two most important phenomenon that we need to remember about electricity and magnetism. And James Clerk Maxwell comes along in 1873 and writes down a set of equations which ties it all together. What's important about this for us immediately is inside those equations, he deduces that this changing electrical field creating a magnetic field, if that changing electrical field can create a changing magnetic field, then of course the changing magnetic field will in turn create an electrical field. But if that in fact is a changing electrical field, it'll create a changing magnetic. Yeah, you get the idea that if you can start off with a properly kind of changing electrical field, you can create what he saw mathematically was a wave, an electromagnetic wave. He went ahead and calculated from his equations from pure theory what the speed of that wave would be. In 1873, he calculated the number, mathematical calculation, and it turned out to be the speed of light, a speed which has nothing comparable in the universe. Not in 1873, and basically not much now. There is nothing that goes like that. So this is either the greatest coincidence in the history of the world, or these electromagnetic waves of Maxwell's theory are in fact light waves. And it didn't take long before these waves were created in the lab. Okay? And the person who did that was Heinrich Hertz in 1873. I'm sorry, 1888, 1887. And what he did, how he did that was to create an oscillating charge going up and down like a spring. He's got a circuit that'll do that, pumping energy into that circuit, making the current go up and down and up and down. And therefore the charges are going up and down and up and down, going up, going faster and faster, then stopping, turning around, going back the other ways, faster and faster to the spring until it finally gets to the bottom, slowing and stopping, going up and down, very much like a spring action. That's a changing electrical field. That a changing electrical field, according to Maxwell's theory, will create an electromagnetic wave, which Hertz showed was the case. He was the first one to create waves at a low frequency, the best technology he had. He couldn't get those charges going up and down very fast. nothing like the frequency of visible light, but he did create radio waves. Waves right now that we still use in a band for TV transmission. And so we finally have, here coming at the time that we're talking about now, in the time of Rutherford, we have the full electromagnetic spectrum. Okay? Here's where Hertz created his waves. The ultraviolet and infrared waves were discovered very much in the same time as Young's experiment. Very interesting story, which we don't have time for. Here are the X-rays of Röntgen. Here are the gamma rays of Villard coming from radioactivity. And we finally have an understanding of where visible light stands in this entire, what's called an electromagnetic spectrum. Okay? All these waves are light waves. They all have exactly the same properties: interference, diffraction, reflection. They all are identical. What's different about them is their wavelength and or their frequency. Right? But they always multiply up to the speed of light. So here on the top, here are the wavelengths in nanometers. Radio waves can be 1 meter long, can be 1,000 meters long, to visible light, which is measured in hundreds of nanometers, to gamma rays, which is 100,000th of a nanometer. A very, very short, very powerful wave. And here are the frequencies. The frequencies can be down to thousands of, millions of hertz, megahertz, to billions of hertz and trillions to 10 to the 24 cycles per second, the highest frequency of gamma rays. Okay? It's the equivalence of wavelength and frequency. Okay. I didn't get as far as I wanted to, but let me just, and I have a few minutes, let me just get this started, because we finished with the properties of light, generic properties of light. We're now ready to focus in on the property of light, which will give us the quantum hypothesis, the quantum theory of a quantum of energy. So let me just go through this one last slide and we'll stop. We know that heat creates light. Yeah, okay. Observationally, we know that. And the hotter the object, the light will change. We'll go from a red hot to a yellow hot. We'll actually even go so hot that we call it a white hot. What's going on? Well, as is always, in any natural phenomenon that's giving off light, it's not giving off one wavelength. It's giving off a spectrum of wavelengths, always. Virtually all natural phenomenon gives off a spectrum of wavelengths. And here's what that spectrum of wavelengths would look like. For something very cool, the spectrum would look like this. Maybe the highest wavelength here. Frequency is being shown. Sorry, not wavelength, they're showing you frequency. Here, the highest frequency, the brightest frequency would be in the red. And so this thing would be red. As the thing gets hotter and hotter, the 1,000 centigrade, 800,000, what happens to this spectrum? It moves. First of all, they get higher, they get bigger. There's more light energy coming out. And we see that the whole spectrum is moving to higher and higher frequencies, moving from the red to the orange, to the yellow, to the blue, to the violet. Okay? And so finally, when we get to a white hot, there's so much light coming out from all of the visible colors that we know when all the visible colors hit our eyes simultaneously in the proper way, we see white light. Okay? That is the definition of white light. It is simply the combination of all the colors coming together. This pattern was of great interest to the scientists of the late 19th century. They're trying to understand this phenomenon. As the temperature of things got hotter and hotter, you got different spectrums. Here's the wavelengths of the distributions, and here's the brightness, the intensity. And you simply made a graph. And at different temperatures, you got different graphs. Could they understand these graphs? Could they predict these graphs? Could they create a theory which would predict these graphs? The bodies that were making these this light was called black body, and so therefore the spectrum that were being produced was called black body spectrum. And we'll get into all of this next time. All right. Greg, do we have any questions outstanding before we go?
Peter, we have no questions. Carol Reller commented on Mosley's death. And
Yes.
in that, she said that Isaac Asimov noted that Mosley's death, quote, might well have been the most costly single death of the war to mankind generally.
Yes, yes, yes. He was just a brilliant young man. That work that I described, he did that all by himself. He's working in the lab at night all by himself, designing and setting up this incredible experiment to show the significance of the atomic number. And then he has these conversations with Bohr. Bohr tells him about his theory of the atom and says, oh, what I've done over here, I think I've got tremendous evidence for your theory, really. So I'll tell that story when we get to the Bohr atom, hopefully next week.
And Peter, a couple comments came up while you were talking. Andrew Sherman commented, so the light we see is actually pulsing.
Oh, no, the light is not pulsing in that sense. The brightness of the light could be quite, even, quite sustained. No, what's happening is when you're looking at this light, you have to realize more than one color is coming at you at the same time. And if you wanted a graph of, say, all the colors that are coming at you at their different brightnesses, that's what this looks like. That's what this graph is depicting. At the different wavelengths, these are the different brightnesses that are coming out all at you at the same time. And the composite color that our brain puts together is a function of the various colors that are coming at you, okay? So here is sunlight right here, okay? This yellow line here. This is sunlight. Notice that it peaks in the visible, but there's lots of ultraviolet light coming out. There's lots of infrared coming out. But because these colors are coming out in this way, sunlight appears to us as white light. The sunlight is constant. The sunlight is steady. There's no clouds, but the different colors have different brightnesses. I hope that clarifies that.
And Peter, one last question from Bill Gunther. Does the trough on a wave always equal the crest?
For a simple wave, yes. For complicated real waves, no, not necessarily. But the waves that we'll be using, the idealized waves, like the sine wave, yes, they will always be the same.
And Peter, another question came up from Andy Chapman. On the graph you showed of Mosley's discoveries, what would have been the label/units on the y-axis?
Those were the square root of the frequencies. That peak frequency, that spike frequency, he was able to measure those frequencies. He took the square root of that number and he found they fell along a beautiful straight line versus atomic number. And that told him atomic number wasn't some arbitrary number. It was a fundamental characteristic of the atom.
And that is the last question.
Okay, I'm going to send out an email, guys. I'll be giving a talk to the astronomy group of Vermont, a local group that Claudio, many of you know Claudio, our great astronomy teacher in Call. He invited me into the group, and I've been part of the group for a year. I gave a talk a year ago. I'll be giving a talk on Tuesday on cosmology. So my message is particularly for the bunch of you who took the cosmology course last fall. I'll be giving a talk on one of the open questions of cosmology that, in fact, we did touch upon at the end of our course. So it's next Tuesday, and I'll be sending out a link to all of you, inviting all of you, any of you who'd like to come and watch that in real time. But it'll also be eventually out on the YouTube channel. I thought that might be of interest to some of the old cosmology students from last term. Okay, guys, have a good week. I'll see you next week.
Thank you.
Hey, bye-bye.
Thank